So this is the full or final version of the in-class activity that we would normally do, simulating conduction of an impulse down a neuron and then contraction of skeletal muscle fiber. So once again, this is our neuron. Here we have the soma or cell body. We're going to pretend that there are dendrites coming off of here. Our axon, our telodendria ending in axon terminals. This is our synaptic cleft. And this area down here represents a muscle fiber. Here's our sarcolemma in red, which then is continuous with the T-tubule that goes down into the muscle fiber, which is adjacent to the sarcoplasmic reticulum, which houses calcium in our muscle fiber. This is actin, covered by our troponin, tropomyosin complex. So these green guys are the troponin, tropomyosin is the red beads, and then this is our myosin filament. We have our calcium represented by little cows. We have sodium represented by salt shakers, potassium by a banana, acetylcholine by coelacanths, once again calcium by cows. So at the beginning, before we've conducted an impulse down the neuron, all our channels are closed. Our sodium is going to be extracellular, so we have sodium outside the cell. Our potassium is going to be intracellular. Our calcium is going to be extracellular when we're talking about our neuron. And then in our muscle fiber, the calcium is going to be housed in our sarcoplasmic reticulum. Our little rubber ducky here is our ligand. So what's going to happen is a ligand is going to bind a receptor on the dendrite, and that is going to open a channel. For this example, this is going to be a sodium channel. So remember Nike, sodium in, potassium exit. So sodium is going to flow into the cell. Sodium is positive. So it is going to bring that resting membrane potential, which is normally negative 70 millivolts. It's going to make it a less negative value, which means it's depolarizing it, making it less negative. When we have this happen in the cell body or the dendrites, it's called a graded potential, because the further we get from the stimulus, the less the effect is going to be of that stimulus. If that graded potential is large enough to depolarize the membrane to threshold at the trigger zone, the threshold is reached, usually negative 55 millivolts, then that is going to trigger the start of our action potential. What's going to happen is we have voltage gates on our axon. Sodium voltage gate is going to open. Sodium is going to flow in. Voltage gated sodium channels are going to open. Sodium is going to flow out. And this is going to continue, sodium in, potassium out, sodium in, potassium out, all the way down the membrane. So our action potential is going to travel all the way down the axon to the telodendria, and then that action potential arriving at the axon terminal, that depolarizing force is going to cause this voltage gate calcium channel to open. Calcium is going to flow into the axon terminal. That's going to trigger exocytosis of acetylcholine into the synaptic cleft. Calcium is going to flow in, our acetylcholine is going to flow into the synaptic cleft. Acetylcholine is then going to bind the acetylcholine receptor on the sarcolemma, the muscle fiber membrane. That is going to trigger opening of that acetylcholine channel, which is going to let sodium flow into the muscle fiber. That is going to cause a depolarization of the sarcolemma, and because this is an excitable membrane, an action potential is going to be generated. It's going to travel from the sarcolemma down the T-tubules because they are continuous, and that arrival of the action potential at the T-tubules is going to stimulate the sarcoplasmic reticulum to release our calcium. Sorry, this is hard to videotape while I'm moving things. So then our calcium is going to bind to our troponin, and that binding is going to pull. It's going to change the shape of the troponin tropomyosin complex, which is then going to expose these active sites on our actin. That exposure of the active sites on actin allows the myosin heads to come in and bind to the active sites on actin, and then actin and myosin can slide past each other, allowing contraction of the muscle fiber. Now, if this axon was myelinated, we're going to add some myelin here. Then this action potential can actually jump from node to node down the axon, which makes its travel much faster, and that is called saltatory propagation. If we do not have myelin present, then that action potential has to travel the entire length of the membrane, which is slower, and that is called continuous propagation.